an accelerator project that I did over the winter quarter to update some open source software. I'll begin just by some acknowledgement and disclosure. First of all, the work that I'm going to tell you about was conducted on the traditional lands of the Coast Salish people. Secondly, this work that I'm going to tell you about was supported by the eScience Institute through their Data Science and AI Accelerator. They didn't give me any money for it, but they gave me a lot of support. My other recent research support comes from these organizations, and you should expect people who talk to you to tell you who's paying for their work, whether it's the things that they're telling you about or other things they've been doing. Because I got 50 minutes to talk to you today, all of the other accelerator projects are just doing like a half session. I'm not just going to tell you about our software and its update. I'm going to spend some time putting it in context. And it's so fun to take this global health stuff and bring it to a broad audience. I encourage you to ask questions as we go. We've got plenty of time, so if there's something that I'm talking about that's got your interest, you want to know more, just jump in with a question. And we're trying to record this, so remind me to repeat your questions. If you ask a question, I'm going to repeat it and then answer it, if I can. So what I'll tell you about eventually is this verbal autopsy software, but I think it probably helps to know what a verbal autopsy interview is, the thing that this software is trying to process. And instead of just jumping into that, I'm going to try to motivate it by saying why I want to do a verbal autopsy interview, which is cause of death prediction. And since I've got that full 50 minutes, I'll start at the beginning by saying why I want this cause of death prediction, which is for the global burden of disease study. Sound good? So the first point is the global burden of disease study. And if you have not heard of this before, don't worry. When I joined the Institute for Health Metrics and Evaluation as my second postdoc in 2008, I also had not heard of the global burden of disease study. I kind of heard of it at the same moment as I landed in the middle of it. And what it is a comprehensive epidemiological study that attempts to describe the mortality and morbidity of every disease everywhere. Also injuries and risk factors, globally, nationally, regionally, and looking at time trends starting from 1990. And it's supposed to make comparisons possible across populations. Now, I mentioned funding. The big funder of this work, since really it started at UW in 2007 or 2008, right around when I showed up, has been the Gates Foundation. And so they want to know about this to guide their investment of Bill Gates' fortune to the tune of about $9 billion a year. You might have heard, for example, they're really interested in eradicating malaria. So this study can help them understand how are they doing in that. What did malaria look like in 1990? How did that change in 2000, 2010, 2020? Are things going well now? And we're always updating it. Our most recent update you can look at online is from 2021. So you can imagine there's a lot of pressure for us to like say what's happened in 22, 3, 4, 5, all coming. But the really cool thing about the global burden of disease study is that it lets you compare between different diseases and injuries. And so while it would be a real triumph to eradicate anything, you might say, we've done a great job on this or that disease. How does the burden of malaria at this point compare to some other major health problem? I don't know, the burden of cardiovascular disease, let's say, or car crashes. And when I would go back to my friends from my grad school, from my first postdoc, and tell them about what I was up to now that I had gotten into this health metrics research, they were all like mathematician types. If they were doing anything applied, it was maybe applied to theoretical computer science. And when they engaged with it, they would really get into like the metrics and the definitions. Like you're measuring disease burden. What are the units of that? Obviously, it's not kilograms. How do you even quantify such a thing? The answer, at least at IHME, is in years, disability adjusted life years, or DALYs, to use the jargon. And this is sometimes called a summary metric because it combines the years of life lost. That's when someone dies from malaria before their ripe old age, how many years of life were removed from the population because of this. And it's combined with years lived with disability so that we can make these kinds of apples to apples comparisons between things that kill like malaria, HIV, TB, and things that don't kill but affect a lot of people for a long time, like lower back pain or anxiety disorder. So it's a way to look at both the things that kill and, if you like, the things that ill. And putting this in years is really convenient. It's not easy, but it gives you a picture of the global composition of disease burden. And if you're kind of a visual thinker about this stuff, like I am, this is one of the images of disease burden that I think would be great for you to have in mind. This visual form is called a tree map. It's a glorified pie chart. You all know pie charts where each wedge of the pie represents the amount of something. So a tree map is like a sheet cake. Each of these rectangles represents the amount of something. And the cool thing about this visual form is that you can organize your stuff hierarchically. So this green wedge at the bottom here is all injuries grouped together. And you can maybe, depending on your vision, see the big wedge within that, road traffic injuries. In blue here is what's often called non-communicable diseases. And you can see a big wedge in there, which has our jargon IHD, meaning ischemic heart disease, really meaning heart attacks. So you can see, for example, in the global picture, I didn't write it on this slide, but this is from 2010. Now it's getting a little bit dated. From some years ago, the burden of ischemic heart disease globally was probably a bit bigger than the burden of road traffic injuries. And this red section here, you can kind of think of as everything else. Sometimes for shorthand, I'll call it infectious disease, but it's not all infectious. It's kind of like all the stuff that the Gates Foundation is particularly obsessed with. It's sometimes thought of as the diseases of poverty. You know, it's all the stuff that is pretty unequal, how it's affecting different parts of the world. But that misses a little bit because a lot of the stuff in blue is also a big problem in a lot of the poorer countries in the world. So it would be a mistake to think that ischemic heart disease was not a problem in India or in Africa. It's just that there's also a lot of other problems there. Where's the one I kept talking about? Like malaria, which is not at all a problem in the United States. If we ever have a malaria case here, it's super exciting for the infectious disease doctors. And it's somebody who was traveling and got malaria just before they came back. This visual form has an interactive version. And if you were to search with your favorite search engine for GBD compare, you would probably find the interactive version of this, which is super fun. If I had more time, I'd probably do a little like test drive around in it because it's a little hard to find some of the different features that are hidden away there. But when you look at a graph like this, no, I'll come back to that. You're mostly like a data science audience, right? So I think probably my guess would be, 1 out of 3 of you, when I was telling that story before, was saying, what are even the units for measuring disease burden? Well, let me simplify that down by saying a big part of these units is saying, what's the cause of death? Because that's how we're going to split things out into the years of life lost. And on that previous slide, there were a couple things that really are about the years lived with disability. Low back and neck pain is a big one here. Actually, that was the big surprise from this particular iteration of GBD. In 2010, we first put in low back and neck pain, and everyone was pretty shocked to see it of similar scale to like strokes because no one had ever measured it in this apples to apples comparison before. Putting aside things that don't kill but affect a lot of people for a long time, like pain, like unipolar depression, like migraine hidden in there. If we wanted to get the first part of this, that's a really important part in a lot of settings, we might just be looking at cause of death prediction. And so For people who are in a data science audience, I think you might be interested in thinking about something besides the metrics in this, which is like, how did I inform those things? So as I was saying, there's an interactive version of this. It's regularly updated. The previous one we were looking at was from 2010, but this is the most recent one that's now publicly available. It goes up to 2021. And I use this interactive version to also slice and dice a little bit. I'm still looking at a global context, still looking at all sexes, but now it's focused on what in global health is often called child health, under 5-year-olds to be specific. And it's focused on deaths. So I'm not including that part about the non-fatal. I'm just looking at what kills globally. You can see a pretty different picture there. For example, heart attacks are not visible in this slide. Uh, Neonatal is visible, and that's kind of a funny one because that's not really a specific cause. That's more like an age group. So a good portion, globally about a quarter of these deaths are ones that happen during the first month of life. And there's actually sliders that if I had this interactive version and have more time, I'd click on this, show you the advanced options, drill down a little bit, but kind of we're not very accurate about what's happening during this neonatal period. So we hide it, and only for the experts can you dig in and see that inaccurate information about what's happening in the youngest ages. To be compared with like congenital malformations, that's one that I think we're pretty precise on, and also has some drill down information if you want to dig in to find out where the specific congenital malformations are. Yeah, I decided not to demo in this time, but I can't resist like calling out how important it is to demo. Some users have said things like, it takes a while to get good at finding your way around these tools. But once you do, they are amazingly informative. So it's like faint praise from one of our big supporters. The point of this is, if you have this kind of information, it's really useful for trying to do something about it. So there's something called the Sustainable Development Goals. This is a bunch of global targets that different countries pledged to work towards. It goes back about 10 years and is a timeline that we're heading for, checking if we've made our goals in 2030. We're not on track to make our goals globally, although the specific goal of reducing child mortality, like we're close. So one of the things that I think is really useful about this GBD exercise is if you're thinking about a particular place, in this case, I've focused the estimates on South Sudan. Can you see the differences from what we had before? I don't have an easy way to like flip back and forth between them, but neonatal is perhaps a little bit smaller, but malaria is a lot bigger. And if you were trying to figure out what to do about child mortality in South Sudan, you might be drawn to this box PEM that wasn't as visible on the previous slide. That, if you were on the interactive version, you can mouse over and find out what it stands for, is protein energy malnutrition. So basically, there's some social exclusion problems happening in Sudan. There's some problems with food distribution. There's kids dying because they don't have enough calorie intake to eat. And that's something that there are really good ideas about how to treat. There are really good ideas about how to prevent. So if you were looking at South Sudan, say from the perspective of the South Sudan Ministry of Health, trying to figure out what to do there to bend that curve and meet the Sustainable Development Goal about child mortality, I think this kind of tree map might be really helpful in saying like, okay, here's the kind of thing that we might want to do. And I'm going to flip this slide to just a different location, and you see the different sizes change. Here's Fiji. So I'll flip back and forth a couple times just so you can like have a little persistence of vision and see how they change. In Fiji, you can't see that PEM box the same way, but there are some other things that really popped out. One really interesting one is STI. And I bet that's an acronym that you do know, but you're saying, wait, in child mortality, do I know that? Are we talking about the same thing as like sexually transmitted infections, the way we learned about in high school health class? Well, yeah, but this is what infectious disease docs think of as vertical transmission. of especially syphilis. There are things that are sexually transmitted infections that are then passed on in utero to babies and then can be a big problem. Also, something that, we have very good treatments for. So if you were thinking about how to bend the curve to go for those sustainable development goals in Fiji, you might be drawn to a very different sort of strategy than if you were thinking about it in South Sudan. And the Ministry of Health in Fiji, maybe looking at information like this, would say, what we really need to do is be screening in pregnancy care for sexually transmitted infections so that when we find somebody who tests positive for syphilis, we can make sure to treat that and make sure that we're addressing it before it becomes a problem for their baby to be. Now, since you're a data science audience, I think maybe you're interested in the metrics, but you're probably also pretty curious about the data. Like, do we know what we're talking about in all of these boxes when we're driving it around to all of these different locations in the world? Well, no. Short answer, no. We know it in some places, and we're going to have to use models and statistical methods to fill in the gaps in others. The best source of data for making one of these plots comes from death certificates. The jargon for this is from vital registration systems. And so whenever there's a birth, we want there to be a birth certificate written for it. And whenever there's a death, we want there to be a death certificate written for it that says what went wrong. Ideally says, here was, the immediate cause of death, and we can trace that back to what we think is the underlying cause of death. I've been kind of sizing up this crowd, and are there any people in the audience who write death certificates as part of your job? Well, sometimes there are in these audiences, and as you continue your educational and professional journeys, if not you writing them, you're going to meet people who write them. And what I'd like you to pass on is that somebody does look at these. When there are people in the audience, they're often surprised to know that anyone ever looks at these death certificates because, like, in a US hospital, it seems like this bureaucratic task that no one cares about. But this is the main source of information for making those tree maps we've been looking at for the last 10 minutes. So somebody looks at those. When you meet somebody who writes death certificates, tell them I say thanks for writing them. And tell them I say, I know it's hard, but I really hope they're going to do their best to write something accurate and intelligible. Question? You do not. The question was, do you have to have an autopsy to get a cause of death? And the answer is no. The clearest times when that is a no is when there's an injury that led to a death. So when we're getting into the data, which actually I should have done a lot more for an audience like this, there's this thick manual called the International Classification of Disease. It's now on volume 11, although because we're the United States, we are still using volume 10 in all of our routine systems. But it has very detailed breakdown of what led to a injury, of what led to any disease. And this is what goes on a death certificate. So there are some cases, I don't know, it's like, it's serious, but it's funny how specific it is. But if someone was bitten by an orca and that led to their death, you would know it. You don't need to do an autopsy. You can put in a very specific underlying cause of death from this contact with a non-venomous animal, specifically a sea animal, specifically a killer whale, without any kind of physical examination. And on the other hand, there are some things that are really important to know from a public health, global health perspective, where it's not like the physical autopsy that's going to tell it to you. It's more like the pathology reports, and the kind of like tissue cultures and examinations. Hepatitis is an example where it's like there's very different things going wrong if hepatitis A, B, or C is the thing that's killing people. But from, even a physical autopsy, all you can tell is like something went wrong with the liver. And so it's really the kind of like biological and chemical analyses that are going to help people figure that out. And exactly where we're going with this, so thanks so much for asking, is what about all of these places that are grayed out in this map? I mentioned that Gates Foundation is the big supporter of this. This is where they're most interested in. Well, there, we sure don't have physical autopsies. we don't even have death certificates representing a physician's best approximation based on whatever data they had available. Well, this is where the verbal autopsy comes in. And this is a term of art that makes it sound fancy because the kind of alternative way to describe what a verbal autopsy is to say, go ask. It helps with, getting people on board for one of these ideas to have some jargon to call it by. In a verbal autopsy, someone who has a sort of semi-structured questionnaire shown here finds a person who's familiar with the final illness of the deceased, and they go ask. It's about a 20, 30-minute interview about the different things that were going on during that final illness. I've actually got a slide that says all this. I might as well put it up while I'm talking you through it. And so this questionnaire includes both structured or closed form questions, as well as open questions like just tell me in your own words what happened. Here's another picture of it happening. And there's really two stages to the process of figuring out what people are dying of using the verbal autopsy. First, this interview where you go collect the data. And then secondly, figuring out what happened based on the interview, which traditionally has been done by expert physicians, and not just any physician, but physicians who are familiar with the kinds of illnesses happening in the population where the interview is collected. So going back to all of these doctors you are going to interact with eventually one day who fill out death certificates, no one likes doing this work, especially in these places where there's not enough doctors. The doctors who do work there and have expertise there would much rather spend their time trying to save the lives of people who are not yet dead than reflecting on like what went wrong, possibly what they did wrong that led to one of these deaths that has happened. That said, from a public health perspective, going back to that kind of like imagining how a Ministry of Health might make plans to bend curves to meet sustainable development goals, it's really important to know what's going on. So the history of this approach, the verbal autopsy, goes back to the 1950s, goes back to some field workers in a project in India who, when doing this, came up with the jargon that we're using, verbal autopsy. And it really took off when the WHO did some reporting about how it was working and said this idea of having lay reporting of health information by people with no medical background could be useful for figuring out what the underlying causes of death are. Some milestones in its development include this really epic study in India deploying it, and then the sort of study that was going on really centered at the University of Washington when I switched into this field called the Population Health Metrics Research Consortium study that was basically a validation of these methods. And since then, based on having some, from a machine learning perspective, let's call it labeled data, we and other groups have been able to make questionnaires that really ask the important questions, use another cool UW technology to make electronic data collection for this. Who's heard of Open Data Kit? This was like a really exciting thing coming out of the UW computer science department 15 years ago. But the grad students who did it graduated, started a company and used it. And we've got to get them coming back to UW just to make sure everyone knows that this whole cool data capture platform is a UW product. And then the part that I'm going to throw back to is automated methods for the analysis of these verbal autopsy interviews. As I was saying, ideally, you have physicians read it. They have to be physicians who have really specialized knowledge, and they don't want to do it. So it would be great if we could get computers to do this instead. Can I call that artificial intelligence? I think I'm going to go for it. The kinds of things that we're looking at when we actually look at these verbal autopsy interviews are shown here, just to give you some idea of the kind of stuff we're talking about. So it has questions like, did blank have fever during her last illness? And for how many days or months before the death did the fever start and end? Those are the ones I was calling structured questions. It's also got unstructured questions, like we'd like to hear the details about everything that happened during the last illness, starting from the beginning and also about what happened during the final hours. And that's something that in a pencil and paper interview, the interviewer is just trying to scratch that all down, writing out what they're hearing. This is the sort of structure for that validation data set that I mentioned. It was in 5 different sites globally. And the way it worked was a death would happen where there was enough information, say in the hospital records or in an injury report, to be really sure of what the underlying cause of death was. And then there was a medical data extraction form recording that was sent to the study coordinator, who then sent out a VA interview team. The VA interview team didn't know about what that underlying cause of death was or any of that information on the medical data extraction form. And so they could go do the verbal autopsy as if it was happening in practice without that background knowledge of what the underlying cause was. But then when we put those both together, that's how we get this labeled data for seeing how well physicians could do it, or testing some existing method for automatically predicting cause, or training a machine learning method to see how well it can do. And this is just a little summary of what's in it. The important thing here is that those groups that were collecting this got over 12,000 labeled verbal autopsies. We designed it so it was split up by ages, and we knew going in there were going to be different causes that were important in these different age groups, possibly different methods or different accuracies for them. It's also stratified by like level 1, we were really sure of what the underlying cause was, and level 2, we were just pretty sure. And this is all openly available data. So if you're hearing this and you're a data scientist and you're thinking, that'd be an interesting thing to explore in one way or another, well, have at it. What you'll find if you download it and figure out how to interpret it is information like this. And so again, knowing that there aren't people who fill out death certificates in the audience, I'm going to guess there are not a lot of people who want to test their clinical acuity by seeing if they can figure out what's going on with this particular patient. But just to give you some thinking about it, the kind of challenge that we're putting to a physician or putting to an AI when we've got the verbal autopsy interview data is to say this: what was the underlying cause of death? This deceased person was a 53-year-old male. They had a history of asthma, heart disease, hypertension, and during this final illness, their symptoms included ankle swelling, puffiness of the face and all over the body, and a cough that produced sputum. They also had difficulty breathing, which was on and off, but worse in the walking position, and a more than usual protruding belly. They also used tobacco. They also drank a small amount of alcohol, risk factors that are sometimes relevant, sometimes not. And then in the tell us in your own words what happened, that included some keywords you might be interested in: asthma, breath, heart, lung, swell, water. Would anyone like to give me their prediction? What is the underlying cause of death? Know that I can check your work because this came from that PHMRC validation study.
Blood clot.
Blood clot, heart disease?
Related.
It's got heart in the free text. And this goes back to like the absolutely ridiculous simplicity of the kinds of natural language processing that we were doing when we were working on this 15 years ago. So the underlying cause in this case is a hard one. It's chronic obstructive pulmonary disease, COPD. And even people who are like med students really up on their game and are friends of mine, so comfortable enough to tell me, are like, that doesn't sound right. Well, that's why this is so hard. So the heart stuff idea is right. And more than usual protruding belly is something that people who are going through med school learning about it will tell you. That really makes me think heart failure. But that's what's so hard about all of this, is that the cardiologists deciding how to categorize diseases for the purposes of global burden of disease study say, well, no. Heart failure is an intermediate cause. There's always some underlying cause that leads to the heart failure. In this case, COPD. So with that in mind, this is a little bit of a brag slide about how well different methods work. Once we had the validation data, we were able to come up with what I'm going to generously call an explainable AI method, tariff, which measured both in terms of like individual level prediction, like basically this is called chance corrected concordance, but basically what fraction of predictions did I get right? Tariff is better than the previous existing automatic method. And actually, it's even better than doctors doing this task. And it's not the individual level prediction that's important to me. It's actually, have we predicted well at the population level? Remember, what I want to say is like, what are the leading causes of death? What should we be focusing on if we're trying to bend that curve? And so it's really the position on the x-axis in this visual figure that gets at what's doing really well. And you can also see that death certificates are still far superior to this verbal autopsy method. So if you have doctors, if they're writing things down as they encounter patients and their deaths, that's still superior. But actually, AI methods can, at the population level, do about as much better than physicians looking at verbal autopsies as physicians writing death certificates when they have the chance to examine patients are able to do better than the AI method. So that's my brag slide. But it really, I think, is time to start telling you about the software, the sort of incubator project that led them to invite me to talk to you today. Any questions about any of this before I get into verbal autopsy software?
What is the difference in the population level versus the
What is the difference between population level versus individual level? Yeah, great question. So when I think about validating all of these different methods, the easy thing to think about is the quality of the individual level predictions. The underlying cause was COPD. Did I get that right? No. Thank you for trying. You were close, but we're going to count that as a no. And then basically what fraction of those are predicted right? That's what I'm thinking of as like an individual level prediction. So there's a little bit of a difference because of this chance correction, but if we're predicting for 50 causes, then if you were just guessing randomly, you'd be right 2% of the time. So you can just think of this as saying death certificates with healthcare experience basically means we only have death certificates for people who died in a hospital in Mexico City. They were, when compared to that gold standard, right about 75% of the time. That's not what's most important for me when I'm thinking about global burden of disease estimates. In that case, really what I want to know is that population level prediction quality. It might be okay to be wrong about some COPD as long as I'm also wrong about some ischemic heart disease and it kind of balances out. If you think about it in terms of a confusion matrix, it's like the y-axis is how much is on the diagonal, but the x-axis is getting a little bit more complicated about how much the marginals kind of correspond. And so that one's kind of weird. Like in a lot of machine learning classes, I haven't seen something like that. We kind of had to make up our own metric to get something that was meaningful for our population like that. And it's easy to mess up. So I didn't put that in this talk, but invite me back if you want to talk about population level prediction sometime. I think we have a pretty good way to do it. And so when we say we're like a 75 for the CSMF accuracy and death certificates are like an 85, basically what we're saying is on a scale from 0 being the worst you could do to 100 being the best you can do, we're like, a B minus C plus range on that scale. Other questions based on everything we've been talking about so far? It is always fun to get a question from an audience like this.
So like I know a little bit about COPD. So like it inhibits venous blood return to the heart. So just is that what your software kind of goes hand in hand with like causes of?
How does the software say COPD? First of all, it doesn't say it that well. So that was a really hard one for my software. What it's doing is in the tariff method at its heart a machine learning approach. So it's looking at associations and saying, okay, I've seen this association in the data I'm trained on. So when I see it in data that I haven't seen before, how should I interpret it? And it's really a glorified logistic regression. It's got a lot of affordances for robustness. It's got a lot of different possibilities for its prediction. But in the end, it's doing not much more than saying for each cause, for each symptom, here's a score that says seeing this symptom makes me this much more likely to think it's this or that cause. And based on the data that we saw from that validation study, then we're going to say that really to be compared with previous methods where they didn't have that kind of validation study and they had to use that kind of clinical perspective, like, well, malaria is a febrile illness. If someone says there was fever, then they had malaria. Turns out there's always fever. So the machine learning stuff that's data driven has a lot of advantage over the kind of like clinical knowledge stuff that works for doctors when they've got all of the information there and are making a differential diagnosis, but is a little bit subtle to turn into an automatic approach. Now, speaking of turning this into an automatic approach, what I've told you about so far is basically like this massive study started in 2007, ended in, I don't know, 2010, even lingered a little bit longer than that to collect labeled data. Then this massive analysis that I think of as kind of a horse race where we compared all of the different methods, doctors, existing methods, new machine learning approaches that we could train because we had this data to see which way could get the best and most accurate predictions overall to, in 2013, releasing an app that implements this tariff algorithm, which was kind of like the one that we favored the most after all of our horse race. It was a little bit worse than my method, but we decided having something explainable where people could understand why it made that prediction was really superior to having something that had a tiny incremental improvement in these accuracy metrics. And I didn't understand it at the time, but in hindsight, that was really savvy of my collaborators to recognize how important it was going to be able to say, okay, and here's some of the thinking behind why this prediction was made for kind of uptake. So we released our first version of this app in 2013, and after a lot of shenanigans and trying to convince people and doing updates on a sort of closed proprietary version of it, we were able to make it an open source app in 2018. And so now if you go to the IHME webpage, you can download the app. It's got some information about how to use it. It's got a version history. And then a bit down on the page, I couldn't fit it into my screenshot, it's got a link just to a GitHub where there is all of the code. When it came out really in 2018, it worked well enough for people to start using it. And I've got a slide that one of my boosters who was really using it a lot gave me all the different things he was excited about. Like he got more than a dozen countries to use it at this point, which was almost 5 years ago. They had analyzed 80,000 deaths with it. Because of the way we had cut down the interview, they were able to apply the questionnaire in like 20 to 25 minutes. And one of the things that he was very interested in was how often it said, I don't know. And in the examples he was using, it was, you know, maybe 7 out of 8 cases, it would say something as the underlying cause. How right is that? Well, you saw on the previous slide, I don't know. But it's was satisfying to them to have that level of like, I know, I don't know. And the problem was it worked well enough that it became hard to convince people to keep doing updates of it. So in 2019, development of this SmartVA-Analyze app really slowed down. There were 3 minor releases in the following 5 years, really sort of a hobby project of a med student who was helping out with these verbal autopsy analyses. From time to time, he'd run into a bug or come up with a new feature that people needed and sort of sneak in on the side of his med school and residency work, on the side of his side job of helping people do verbal autopsies, a little bug fix or a little feature extension here or there. And it wasn't until this eScience Accelerator, the beginning of 2025, that we had finally a major update to the code. And so thanks to the eScience Accelerator, it has been really great to be able to kind of revive this project. Because it's all in GitHub, there's kind of a fun way to see what this has looked like. Now, this isn't totally accurate because early on, I think they were like squashing commits or something. So it was a ton of work to get from the research code that we dumped on this team of contractors to the initial release, kind of like a 1.0 version back in 2013. You can't see that here, but that's when it started. And then there was, a bit of a pause and updates based on this initial reaction to it. And then a really active time based on people starting to use it, saying, here's the things that are working, here's what people need to really get it to the next level, to get to a 2.0 release in 2018. And then this is that big gap that I was telling you about that included like, well, 3 years before the accelerator, a colleague of that med student said, hey, I noticed that you're still on Python 2.0 and that is deprecated. So she started the process of upgrading it to Python 3, but I didn't have the time to test it and make sure it was working. I didn't have the wherewithal to understand the things she was offering. So it wasn't until this January, with the help of this awesome eScience Accelerator, that we were able to merge a pull request, really updating it to this modern Python 3. So excited to get to that point. And besides that update, we also, you can see in here, added what you could call continuous integration. Now, every time someone does one of these pushes to GitHub, or every time someone does a pull request, it takes a bunch of tests, automatically runs them on a bunch of different versions of Python and different OSs, and says, oh, here was a bug, this is something that didn't work in this new version. So it's a way that I can get contributions from people like a busy med student and know quite quickly if this is a valuable contribution to the software. And I've had like a few reflections that I thought I'd share just about the process of how we did it. It's all going to be gone from my memory so soon, but it was a great time while we were doing it. So it's really nice to have a chance to write down some of it. The way we did it was really essential to have weekly meetings. And this was with Brinna and Naomi, who are sort of the eScience sponsors or advisors for this, and me as the main person working on it. And when I had signed up for it, I was hoping that I would be the advisor, and then we'd meet weekly, and between that, someone else would work really hard to push the software forward. So in some ways, I was tricked. But I was tricked into learning, so I think it's a good way to be tricked. Between each of those weekly meetings, it was really on me to push things forward, say, try to get all the tests passing with the Python 3 version of our code. We used GitHub to track all of these tasks and to communicate between meetings about how things were going. And I think that worked really well. And I don't know if the eScience Institute would have even sponsored this project if it wasn't open source software. So this sort of 5-year struggle to get my colleagues to agree to release the source, I think was really valuable to being able to do this sharing and do this getting help. I had a software engineer who worked on it during that update to 2.0, who was really meticulous about making automatic tests. And so that was a great boon to upgrading things to 3.0 when we were able to say like, okay, now that we've made changes so that we think it's going to run in Python 3, let's run these tests and see where it is that we still have some work to do. And then turning that into continuous integration, I think, is going to be a great improvement going forward. And then this one other thing that I had kind of on my mind this whole time was, besides the sort of unit tests and functional tests that are publicly available with all the code, I've also just been collecting up a library of data that people have collected and run the verbal autopsy analysis on over time, so that I can rerun on all of their data every time I make a big change and see if any of the outputs have changed. And that's because when we were doing this update, I didn't expect any of the predictions to change. I kind of wanted it all to be the same. So I'm going to put this up here, but not read through the whole thing, because I thought it would be fun to include in this also a demo. And we're coming up near the end of this time. So If anyone has questions I've left unanswered, make sure you get them in. But should we demo? So this is what the app looks like. How do I get it onto the screen? There it is. And if you open up SmartVA-Analyze, you're met with this interface. The first thing you need to do is find the file that includes the sort of tallied results of your verbal autopsy interviews. And that's going to be a CSV file. It's going to be something that maybe you've created with the Open Data Kit tool I mentioned earlier that these UW students made to begin with. If you didn't do it that way, it's going to be something that you very carefully mapped to have the expected format. And besides that input file, you're going to pick a place for your output to go. I'll just make a new folder here called T. Seems like a thing that's going to be totally clear to me when I look at what's on my desktop in the future. And then you can choose a location. I happen to know that when Nicole was testing the reliability of this approach, she was working in Nepal. And then you can say like, well, I don't want malaria to be included in some of these because as we were saying earlier, you know, there's some places where we think there's really just not a problem with malaria. Nepal actually, let's include malaria just in case. And then start your analysis and away it goes, processing the different data in the verbal autopsy interview. And when it's done, it opens up a folder, which opened on the window you can't see, that includes those results. And so it's got different folders that have different types of results. The one fun one that I'll open up for you while we're doing this is the files in the monitoring and quality folder with names like adult likelihoods. Be cool if you open on the screen where everyone could see it. We'll see. But what this one does is gives you basically a row for every verbal autopsy interview, kind of with a primary key for the subject ID that says the information that was collected, like the age, sex, and predicted causes. And then the cool thing about this is that it also has this kind of explainable AI stuff where it says, well, if it's undetermined, there was nothing that made it undetermined. It was just the lack of evidence for anything else. But for a chronic respiratory disease death, we think it's likely. We're not sure it's very likely, but it's based first and foremost on that pre-existing condition or previous diagnosis of asthma. And we're not sure of that. If you were to give me a second guess, the second most likely thing I would say is stroke, less likely, but the kind of most important indication of that is the sudden loss of consciousness. Is it time for me to stop? So I'll wrap it up there just by showing you the kind of like data analogous to that COPD example we saw before that we have to deal with from each of these rows. And going back to the slide that will let me wrap it up, I will say, in summary, disease burden and cause of death is important for meeting our global health goals. Verbal autopsy interviews are important for filling these gaps. And the eScience Accelerator was super important for being able to update this software, for being able to fill these gaps, for being able to make these decisions. And I didn't mention it in any of this because I got too excited about the different history stories that I was telling. But one of the reasons I was so excited to make this update was so that going forwards, I can see if these modern advances in artificial intelligence give me anything that's totally not explainable, but in any other way is superior to what I've done so far. So I will leave it there. And if you do have more questions, happy to stick around and answer.